Energy and power. Our lesson today is going to be what is power. So what is power? I mean, it's not, you talked about the power of like a president or a prime minister or something. In physics, what is power? Well, that's what we need to know, isn't it? It's something we should have mentioned from Key Stage 3 about power. And power, if we put it simply, is the rate that energy is transferred. It's how fast something can transfer energy. If we remember, energy was the ability to do work. Energy was a way of saying whether things were permitted or not. If there was no energy, the thing is not permitted. So, power, we can say, is how fast something can do work. How fast a force can move an object, for instance. Fits in with our topic. We've defined work and energy. We've looked at specific examples of energy, kinetic and potential. Now we're looking at power. So our spec reference is still the same bit of the spec, and it's up at the top there. Rate of doing work equals rate of energy transfer, and definition for power. So what do we need to be able to do? State which physical quantities are involved in power. How could you develop more power as you go up a flight of stairs? And why is a 100 watt light bulb more powerful than a 40 watt light bulb when they both are at the same mains voltage? So, definition. Power is defined as the rate of energy transfer. It is how fast energy goes from one place to another star. The units of power are watts, capital W, which is equivalent to 1 joule per second. So if we transfer 1 joule of energy per second, that is 1 watt. So remember, we defined 1 joule as moving 1 newton through 1 metre, so that's a small bag of sugar. If I lift it up 1 metre in 1 second, that is a power of 1 watt. We could put that as a formula and say power is delta E divided by delta T, as in the change in energy divided by the change in time. Where the energy is transferred by a force doing work, remember energy is equal to work, so that formula could also become power is change in work over change in time. Delta W over delta T. If we've got a powered object moving at a constant velocity at constant height, the constant height bit important because it's not doing work against gravity. It's only doing work against the resistive forces like friction, air resistance, etc. The resistive forces are going to be equal and opposite to the motive force, whatever force is coming from the engines, whatever's powering it, if it's travelling at constant velocity. Remember, that's via Newton's first law. So the work done by the engine is being transferred to the surroundings. It's heating them up, isn't it? It's transferred the internal energy of the surroundings by resistive forces. The friction between the vehicle and the air is causing the air to heat up. So the energy is being wasted as thermal energy. We would find that the work done per second is force times the distance moved per second. Work done is force times distance, but if we want the rate that work is done, the work done per second is the force times the distance per second. Now we've got a name for those two things, don't we? The work done per second is power, what our lesson's about, equals force times by distance moved per second. Can we work out what that one is? Velocity, right. So, power is force times velocity. For example, say an aeroplane is powered by engines that exert a force of 40 kilonewtons. It's in level flight at constant velocity of 80 meters per second. What is the power output of the engine at this speed? Power is force times velocity, so we substitute in. The force, 40 kilonewtons, is 40,000 newtons, times by the velocity, 80 meters per second, gives us 3.2 million watts, 3.2 times 10 to the 6. If a powered object gains speed, well, if it's gaining speed, there's got to be a resultant force. By Newton's second law, we can say that the amount of resultant force gives us the amount of acceleration because they are proportional. But we know that in any case, the output force of the motor has got to exceed, it's got to be greater than the resistive forces on it. So via conservation of energy, we could say the motive power is the energy wasted per second plus the gain in kinetic energy per second. Because all of the energy's got to be going somewhere. So my engine's making some power, or it's transferring energy from its chemical store in the fuel, for instance, into kinetic energy in the engines, but that amount of power has got to equal where the power's going per second. So the energy wasted, thermal energy to the surroundings per second, plus how much faster it's getting each time, the gain in kinetic energy per second. So, plainly, if I ask you, what is power? Power is the rate of energy transfer, how fast energy is transferred per second.